All right, ladies and gentlemen, coming at you from the Way Happy Studios, the North Side Way Happy Studios. This is Mr. Meyer, and we are doing functions and their inverses. Now, remember inverses. That's where you're like, whoa, what do we do for inverses? That's a function that should cancel itself out in essence. It should be the opposite, like, multiplication and division. They counteract each other. You got addition and subtraction. They are inverses of each other. Squaring, square rooting are inverses of each other. And so we're going to do this with the functions, and we're just going to kind of show how two things. I want you to determine if the inverse is a function, and second thing is I want you to be able to write the rules for the inverse function. In other words, find that inverse function when you switch the x's and y's or change all the y's to x's and the x's to y's and solve it for me. So we're going to talk about these inverses. Now I want you to look at some of this stuff here, like what some graphs look like, what lines look like, what square roots look like, what x squareds look like. Now think about their inverses if you do or do not know them. And could you tell me if their inverse was a function? Well, just like when we think of a regular old graph, pretend you have that square root graph. If you have, or I'm sorry, absolute value graph. If you have an absolute value graph, and you know what that looks like, and you know it's a function because all you've ever done is you've grabbed a vertical line and you've tested it, and as long as it only hits that graph that you made one time, the vertical line, it's going to be a function. Well, there's this thing called a horizontal line test, and it's a little tricky in the fact that you draw a horizontal line test, and just like the vertical line test, if it hits more than once, it's not a function. But it's not telling you if the function you're looking at is a function. It's telling you that the function's inverse is not a function. And so that's the really confusing part, is that a vertical line test checks the function you drew. A horizontal line test checks if the inverse of the function you drew is a function. So that's a little bit crazy, right? So here it kind of is clipped from the book that you will see is that a horizontal line test, if it passes through more than one point, the inverse of it is not a function. And that's really how you check. Look at example 1 as I scroll down. You will see example 1. I say use the horizontal line test to tell me whether graph A and graph B tell me if their inverses are functions. So I really got to pound it in your head, right? Let's call the blue graph A. So graph A, if I asked you if it was a function, you would do a vertical line test. And you would tell me that nope, A is not a function. You'd say nope, A is not a function because it fails the vertical line test. So that's if you're because it fails the VLT, the vertical line test. But if I asked you about A's inverse, then your brain's got to switch and you do quickly a horizontal line test. And all you do on a horizontal line test is you take your horizontal line and you slide it. Now again, this can be kind of hard. We're going to only look at the blue graph. But notice a horizontal line test only touches the blue graph once and one time only the entire time. So I would say, but, a little heads up here, but A's inverse is a function, because it passes the horizontal line test. That's really the question I was asking you in this, but I wanted to talk about the vertical line test versus the horizontal. Do the same thing with equation A, graph B. If you look at graph B, you will notice it will pass the vertical line test. There is no vertical line that would ever hit two dots. So I could tell you that graph B is a function. So B is a function because of the vertical line test. But I can also tell you that the inverse of B may or may not be. Let's see. Oh, that's a horrible horizontal line, I'm sorry. It's a horrible line. In fact, I'm going to have to use now a better one just because that one was so bad. So here is my horizontal line. And look, I can slide that line and look right there where I drew it, it's actually hitting more than one part of the red graph. So I know that it is, in fact, not a function. So B's inverse is not a function. And that's because of the horizontal line test. So vertical line test tells us if the graph we're looking at is a function. Horizontal line test tells us if its inverse is a function, yay or nay. All right. Let me ask you a question about that, and I'll see you on the flip side. All right, beautiful work on that problem. Now let's talk about example 2. How the heck do you find an inverse? So finding an inverse, not a big deal. The only thing you want to remember is that you replace the x's with the y's and the y's with x's because it's a reflection over that diagonal y equals x line. So first thing I'm going to do is I'm going to rewrite our problem here, which we have the cube root of x plus 1. And I am going to now replace all the x's with y's and the y's with x's. So you will see now I have x equals the cube root of y plus 1. And now, I've made the inverse. Well, let's kind of pretty it up. We like these things to say y equals. So let's go ahead and make this say y equals. So the way I'm going to do that is I think I'd like to kind of get rid of this cube root. So I will cube both sides of the equations. And we have x cubed equals y plus 1. And now I will move that 1 over and I will have x cubed minus 1 equals y. That is our inverse. Now if we know what the graph looks like, which I think we do, right? Looking back at the original one, you know that that's a cube root graph and it is going to be left 1 unit. So you should have something that looks like this on a cube root graph. And then the inverse now is a cubic John Travolta graph that is down 1 unit, and it should look something like this. And if you're really a visual guy or girl, you will notice that it should be a reflection over this line, and if it is, they truly are inverses, right? If they are a reflection over that y equals x line, then the graphs are definitely inverses, and you can high-five yourself and say, woo, I found it. You can also answer questions like, is it a function or is it not? Remember, if you want to check if a graph is a function, do a vertical line test. If you want to know if its inverse is a function, do a horizontal line test. So be super careful there. This one would be a function, that red one that we created, so you could write it as a function. In fact, I should probably tell you the notation. If people want to tell you that it's an inverse, they will use the notation instead of f of x, f to the negative 1 of x. That's how I tell people it's an inverse. And so the inverse of f of x would be x cubed minus 1. And that's how I would tell you with notation that it's the inverse of f. So f to the negative 1. What about domain and range? You might notice something silly. The domain of one will be the range of the other. So if I look at the original graph, its domain, the black graph there, was all real numbers. All x's, all real numbers, right? Now, if we talk about the inverse, since it truly is an inverse, that range would now be exactly whatever the heck the domain was. So we would say, well, we got to change the variable. All the y's are all real numbers. Now you could do the same thing for the range of the original. The range of the original graph would be all the y's such that the y's are consistent of the real numbers. And guess what? In the inverse, that flips to become the new domain. Now look at the graph and see if you can figure that out anyway. But it's kind of nice to know that a domain and a range, on an inverse, they will flip. Always something that kind of sneaks up. And that is how you find the inverse. That's how you find the rule. And next, we'll talk about proving. So hold tight. Hey, good job on those. Now, lastly, we're going to talk about composition of functions to see if two functions really are inverses. Sometimes people will come up with two inverses and they will ask us, hey, are these really inverses? And I'll say, I don't know, let's check real quick. The easiest way is to use composition that we learned from last section that says, hey, look, if I take the variable x and I throw it into the function, something should happen and it'll spit out an answer. And when I throw that answer into the inverse, something will happen and it should spit an x out. And if it does, you guys really are inverses. If it doesn't, though, then you guys aren't inverses. And so this is how I would check somebody's work. So a kid comes up and tells me in example A, they're like, hey, look, these two are the inverses. And I say, well, let me check for you. And so what I quickly do is I would just do f of g of x, our good old composition, right? So I would take g, which is 1/3 x plus 1, and I would plug that in to equation f. So I'm going to take all of this and I'm going to plug it right in there and see if that's true. So real quick, I would just take the 3. Now the x changed to 1/3 x plus 1. And then I have a minus 1 on the back. So there I have substituted g into f. I'm using the variable x, right? Nothing fancy, not a letter, not a number, nothing, just simple old x. It's going into one function. It'll be coming out, and it should come out as an x. And if it does, hey, we got inverses. And if it doesn't, I'm a little worried. So distributing the 3 through, I would get 1x plus 3, and then minus a 1 on the back. And as I combine these terms, I get x plus 2. And then I stop and say, uh-oh, something bad has happened. I plugged an x into your equation, and it came out as an x plus 2 after I put it into both equations, both into g and both into f, into the composition of those two. It didn't come out as an x. So bam, something's wrong, right? And so therefore, these are not inverses, and I can tell right off the bat. You could also check visually. I graphed it over here, and if you look, there's the first one, the red line. There's the second one, the blue line. They should be a reflection over y equals x. So look at this. There's the y equals x line, and you can definitely see they're not a reflection over that line. They're just skewed a little bit. So they're pretty close, but they're not inverses. So good try. What about example 2? If I do example 2, or B, same kind of thing. Somebody's walked up, said these two are inverses. I look at it, go, yeah, it could be. Now I got to be a little skeptical. So I'm going to do f of g of x, and I'm going to see if they really are inverses. So f of g, which is 1 over x plus 1. Now again, we're going to go over into this equation. We're going to take the x out. We're going to put all this stuff in its place. So what we do when we get that is 1 over, oh yuck, 1 over x plus 1 minus 1, right? So I got all that in there. Well, cool. The minus 1 and the plus 1 actually are just going to knock each other out. So they're gone. So now I have just 1 over x. And good thing we've done complex fractions, because this is definitely a complex fraction, or what I like to call copy dot flip. I'm going to copy the top. I'm going to change it to dot. I'm going to flip the bottom. And when you multiply that together, you get x. And I jump up and down because I say, look, I put an x in and an x came out. That's awesome. But is it enough for us to believe they're really inverses? Looks pretty good, but sometimes things happen and you're like, well, you know, maybe that was lucky. So the way you can truly check is if you check one way it worked, then it should work the other way also. So if it does work, then really quickly try g of f of x and see if you see the same results. I'm going to be putting an x in. If an x comes out, then I know it's an inverse too, and these guys are definitely inverses of each other. So I'm going to try g of f of x. Now what was f of x? 1 over x minus 1. So I'm going to take that and I'm going to substitute it into there. Oh gosh, this is going to get complex again, it looks like. So I'm going to have 1 over, now substituting in, 1 over x minus 1, and all of that is plus 1. All right, that's a little nasty looking, right? A little scared. I really do not like this part that is complex right here. So can we clean that up before we add one? Because that's just making me nervous. I wish it was just a fraction. So I'm going to copy dot flip. So I'll take the top, copy, change it to dot, flip the bottom, x minus 1 over 1. And notice that gives me x minus 1. Now don't forget this plus 1 that I've kind of ignored. He's on the back end here, and so he will continue to be on the back end. And look at that. The 1's cancel each other out, and I get x. Again, plugging an x in got me an x, and therefore I can say, yes, those two are definitely inverses. You did not lie to me. Have a great day, and I will see you tomorrow. Stay happy.